So it's been about 2 weeks or so since we've looked at this, but 2 weeks ago we learned how to parameterize a surface that's embedded inside of 3 dimensions, or at least we began to develop some tools for doing that. So one of the examples that we did together was, how can I parameterize a sphere in 3-dimensional space by viewing that sphere as the surface of revolution created by a semicircle, and then spin that semicircle about the z-axis. And so ultimately we found this parameterization that looks like x equals the radius times the cosine of the longitudinal angle, the angle theta, the angle that we would describe as the angle around the z-axis, right? The angle which is measured counterclockwise from the x-axis in the xy plane, times the cosine of the azimuthal angle, and that's the angle that we would measure clockwise from the positive z-axis. It's an angle of declination from the positive z-axis. And this parameterization, here's x of s and t, here's y of s and t, and here's z of s and t. If we bundle this together into a vector-valued function, then what we get is something that we would call a parameterization for the surface, right? It's a 2-variable vector-valued function, and s and t, the parameters, sort of specify a location along my surface. And because it's a vector-valued function, we'll give it a name that's boldface like u. So u of s and t equals, and then in a set of big parentheses here, we'll put r times cosine of s times cosine of t. And then r times cosine of s times sine of t, and then r times sine of s. And then put that whole thing in a big set of parentheses. And this is one way to parameterize a sphere whose radius is r. Now, when you did this problem, you made the decision to represent the angle s. Actually, the angle s was the azimuthal angle, so I misspoke on that. You chose to represent s as being measured from the positive x-axis instead of the positive z-axis. So you got a parameterization that's a little bit different. So this is the one that you found for the sphere, which is a valid parameterization. But then by making the other choice of what that angle s represents, if s represents the angle measured from the positive z-axis, that's sort of the convention that is most often used by mathematicians, at least. Physicists sometimes use a different one. But if we use that as the angle s, then instead of cosine in the first 2 terms and sine in the z-coordinate, it's the other way around. So we end up getting r, actually let's call it rho, because that's what the spherical coordinate is going to be named, times sine of s times cosine of t, and then rho times sine of s times sine of t, and then rho times cosine of s. And so this is what I might call this sort of traditional, or the conventional parameterization for a sphere of radius rho. And so this is the parameterization that, when we reinterpret it as a coordinate system for 3 space by letting rho also vary, from 0 to infinity, we're going to get all of 3 space. We parameterize all of 3-dimensional space using spherical coordinates. So we're going to come back to that toward the end of our class today to sort of recall how spherical coordinates work. But when rho is not a variable, when it's not a coordinate, when it's just a constant, then what we're parameterizing is a sphere. And this vector-valued function is an example of such a parameterization. So what we want to do is be able to use a parameterization for a surface as a way to compute surface area on a surface. And so to do that, what we're going to have to wrestle with is how do we get information about area? So how do we get even a little chunk of area on my surface, an infinitesimally small chunk of area on my surface, out of the formula for a parameterization. So once again, the authors of our book do incredible work to attend to the Riemann sum aspects of sort of how we get to integration in the first place in thinking about a question such as this one. And once again, we're going to kind of bypass that great work that they do there. So sorry, authors. And so instead of starting with the preview activity, we're going to jump off from the end of the preview activity and go directly to sort of where does surface area come from? How can I come up with a way to find surface area given a parameterization for a surface? So the idea is this. I'm going to borrow this diagram from over here. That if I take a parameterization for my surface and I look at the partial derivatives of that vector valued function that is giving us the parameterization, then what those partial derivatives are giving me is that just like any partial derivative, they're giving me kind of a slope of something, or maybe we can think of it as a velocity vector of something. Maybe velocity vector is a better way to think about it. Because if I take a vector valued function of two variables s and t, and I take the s partial derivative, for example, the s partial derivative treats t like it's a constant. And so what I'm really doing is I'm treating t like a constant and getting a parametric curve that is a part of my parameterized surface, where s is the parameter of that parametric curve. And so if I take the s partial derivative, what I'm getting is a velocity vector to that surface that points in the s direction, because it's a velocity vector that is tangent to the trace of this surface at a constant value of t. And so I'm getting a velocity vector in the s direction on my surface when I take the s partial derivative of a parameterized surface. Same thing in the t direction, analogously, that I'll get, because I'm treating s like a constant, then I'm getting a trace in the t direction, which is a parametrized curve, and taking the t partial derivative of that is the same thing as just taking the ordinary derivative of the curve whose parameter is t. And so I get a velocity vector that points in the t direction. And so presuming that the velocity vectors are not parallel or anti-parallel to one another at such a point, which a good parameterization will not do, and I put the word good here in quotes, presuming we have what's called a regular parameterization for our surface, then these velocity vectors will not be parallel or anti-parallel, and so they will span a little parallelogram that is going to have a non-zero area. And if we can compute that area, then that area is going to approximate, if my velocity vector is small enough, if I sort of take a small enough approximation on my surface, that little tiny parallelogram is going to approximate a little tiny piece of surface area on my surface. And so the question is, given two vectors, how do I compute the area of the parallelogram that they span? What is our vector geometry tool for computing the area of a parallelogram spanned by two vectors? So we can get the area of this teeny little parallelogram that is on my surface by taking these two velocity vectors. So these are going to be tangent vectors in the s and t directions to my parametrized surface, respectively. And if I take their cross product, what I get is a vector whose direction is perpendicular to both of the tangent vectors. So in particular, that cross product vector is going to be perpendicular to my surface at that point. And its magnitude tells me the area of this teeny tiny little parallelogram on top of my surface. And so that cross product multiplied by ds dt is going to be our element of surface area that we can use to compute the surface area of a parameterized surface. And so the upshot of this is, if I have a parameterization for a surface and I want to know what's the surface area of that surface, I want to set up a double integral of the magnitude of the cross product of the partial derivatives of my parameterization. And then that becomes my integrand. Then I just have to integrate that over whatever range of s and t the parameters are appropriate to describe that portion of the surface that I'm trying to find the surface area of. So that's the setup of what we're about to do.